months of work on computer graphics. So fortunately, there was one of those easels right there. And so I took a colored marker and I said, well, this is what you would see, and this is what we saw, and this is how it worked, and this was the scattering angle, and this is the cross section, and this is what it looked like. And I got honorable mention in a scholarship. So I thought that was pretty good for not having my stuff together.
Well, thanks for turning up today, and Science Sunday continues. Very happy to have this talk today. I do want to announce that I said something earlier in the church service, but my daughter had a baby last night, so we've got a grandson now in the family that I'm pretty proud of. Jane and I are going to be flying out to Seattle tomorrow. I won't be back in time for the next Science Sunday, but Jim Walters will be leading that. I'm sure it's about evolutionary psychology, and we'll make sure we post what the topic is and so on. I think he did a nice talk and got some nice comments last time too, so make sure you show up for that. But yeah, this is Thanksgiving, so I've got some things to be thankful for, and another thing is all you people coming up to Science Sunday too, so thanks so much for coming in, and with that, we'll let you take it away.
All right, thank you. Welcome, everyone. Also want to be thankful, express our thanks explicitly to this church, the DuPage Unitarian Universalist Church. Some of folks associated with the humanist group that I'm privileged to be the president of don't like the term church. We call it our clubhouse, so the DUUC still works, DuPage Unitarian Universalist Clubhouse. And, they provide this forum for us. They provide the internet connection and the AV and all of these nice gizmos and the meeting space, and it's just wonderful. And it's all consonant with the Unitarian Universalists' emphasis on a search for truth and meaning and interconnectedness, and several of the other fundamental principles of Unitarian Universalism are quite consonant with our search for scientific truth in the universe. So we fit right in. We have for about 13 years or so, and happy to be here. So today, I've talked about astronomy and astronomical issues in the past. Mike and I have, and other guests, speakers like Joanne and others have talked in the past about all kinds of topics. I often talk about astronomy. It's one of my hobbies. I am an amateur astrophotographer. In fact, I was out all weekend taking some pictures. And astronomy is really intriguing because there are whole other worlds out there, whole other planets around other stars, and even trying to understand how the stars work and how we came to learn about the way stars work is, I think, a fascinating story. And today I'd like to tell a little bit of that story, a part especially that is frequently and sadly overlooked. There we go. If I have to hold it up here. There we go. All right. Ancient questions about the stars. I should have made the font bigger. What are the stars? What do they mean? Right? Think about astrologers trying to find meaning in stars. Well, one of the things that certainly seems to be true is that you see different stars in different seasons. So what's the cause and effect there? Do the seasons cause the stars? Do the stars cause the seasons? You see certain constellations during certain times of the year, and that helps you understand when it's going to be harvest time or planting time. So it certainly seems reasonable that the stars serve as guideposts to our temporal lives. And, maybe a God put them there just for that purpose, right? There's all kinds of questions and speculations that swirled throughout history about what they are, what they mean. Why do they change? Why do stars come and go season to season and yet remain constant between the same season of different years? And yet there are certain stars that seem to wander around in a kind of unpredictable way, but, well, maybe it is kind of predictable. All these questions, quite reasonable questions. And as all of you know, I'm sure, We live on a planet that has a axis that's tilted with respect to its orbital plane, and that's what causes the seasons, right? We've got about a 23-degree tilt, which is pretty big in the axis of the Earth, and that is why we see different stars at different times of the year, as nighttime brings us around to different skies in our orbit of the sun. So some of you are familiar with the story of Giordano Bruno. Giordano Bruno was famous in sort of modern pop culture as a philosopher. He was actually a friar who speculated that the stars are other suns. And sometimes it seems to be that he gets credit for originating that idea. He was executed in a very brutal way in 1600, and his execution was because of his heretical ideas. Part of his heretical ideas entailed the notion that there were other suns, that stars were other suns, and that they had planets around them, and that there was life on each of those planets. And therefore, each of those planets around each of the stars we see needed their own Christ. And so there were multiple Christs and multiple sacrifices, and he kind of went on from there in his speculations. He happened to be correct about the fact, as it turned out, that stars are other suns, but some of his other speculations were, to put it mildly, inventive. But in any regard, the Catholic Church was not in favor of his speculations and decided that the appropriate thing would be to murder him. So they did that. But he was not the first. Oh, by the way, there's some speculation that Galileo Galilei saw Giordano's execution, because he was Galileo was a young man in 1600, living in the same city where Giordano was executed. So you know about Galileo being persecuted for his thoughts about heliocentrism and whatnot. He had a vivid example of what it means to disagree with the church in his personal history. But in any case, Bruno was not the first to speculate about the stars being other suns. There was Anaxagoras about 500 BCE, and he was a philosopher. He speculated about the nature of the sun and stars. He was interested in meteorites and how they came to be, and and comets. Pretty much any celestial thing was under his purview. And he came up with some interesting ideas, including that the stars are indeed like the sun, but very far away, maybe thousands of miles away. And then Epicurus, Epicurean philosophy. Some of you have read the Pulitzer Prize-winning book, The Swerve. And in that book, one of the things that's talked about a lot is Epicurean philosophy. And the Epicureans believed that the stars were other suns as well. So this notion did not originate with Giordano Bruno. People have been wondering about that for a long time. And that was about as far as it went, besides the effort to, battery must be running low in this, to catalog stars. So about throughout history, Plato is, or not Plato, who is the guy in Egypt, Ptolemy, right? Ptolemy cataloged the constellations, and so the notion of cataloging the stars and denoting how they relate to each other and which stars you can see, and kind of giving them a position in the heavens, as it were, that was something that goes back to ancient times as well. But starting in the 1800s, so the 19th century, the middle of the 19th century or so, with the wider availability of telescopes, and an ability to calculate coordinates vis-a-vis the heavenly spheres, right? Astrolabes and other things that have been used for navigation in the past, gave us the idea of imposing upon the sky an imaginary coordinate system. And so tracking the location of stars with respect to coordinate system, this imaginary coordinate system, became a scientific undertaking. And there was a project led by University of Paris, or a university in Paris, called Carte de Ciel, a map of the sky, ceiling, sky up above. So mapping of the sky. This project started in 1887. The Harvard University, or Harvard College Observatory participated in this worldwide effort to chart the location of all of the stars that we could see. Now, back in that era, they didn't necessarily know that there were more stars in the heavens than we could possibly count, right? But we could certainly see some. You can see throughout the year, if you start counting them and you're in a really dark sky, the naked eye, you can yourself catalog about 5,000 stars. So quite a few of them. And the Harvard Observatory had all this data to go through, because what also happened in the mid and later part of the 19th century was the development of photography. So that was a huge boon to the practice of astronomy. They discovered that you could take pictures of the stars. You hear that sometimes. One of the things I've enjoyed doing is taking pictures of the northern lights when I've been up in Minnesota and Alaska. And I've had people ask me, you can take pictures of those? Yeah, they're real. They're really made of, they emit light, right? So yes, you can take pictures of the northern lights. You can take pictures of the stars. How cool is that, right? So they started collecting these glass plates that were about the size of a sheet of paper, right? These very fragile glass plates that were exposed to the night sky via a telescope, and they made these wonderful maps of the sky. And then the idea was to look and try to extract as much information as you possibly could from these glass plates. And that entailed measuring them. You'd have a micrometer or some other tools to measure the specific position and location of the stars, and then correlate that with this grid that humanity has envisioned, emblazoned upon the heavenly sphere. But that's really quite exacting work. And in a way, it can be tedious unless you love, and there are people who do love looking at stars and pictures of stars. I prefer nebula. I think they're more exciting. But stars are, perfectly cool things, and we're going to learn more about them today. But Harvard, the director of the Harvard College Observatory at the time, decided to hire some staff to help work their way through these photographic plates. And inexpensive source of labor who were competent enough to be meticulous, but fragile enough that you had to keep them indoors. You couldn't expose them to the night air and whatnot. You couldn't ask them to carry heavy plates or move a heavy telescope and whatnot. And that would be the species known as female humans, right? And so these ladies were employed as what are called in the day computers. So you may think, when I talk about, come on. Yeah, I'll get to the computer thing again. I'm getting ahead of my slides. It's fun to tell it as a narrative. So here's Edward Pickering. This was the fellow who decided to hire these female computers. And in the background behind him, you see Harvard Observatory there in the area of Boston, right? Cambridge, a suburb, right? It's across the river. Thank you. She's from that area, familiar with the geography. And so Edward Pickering, who was apparently quite a gentleman, a very, very nice person, very respectful of the ladies, and paid them about half as well as he would pay a man, which was quite respectable in the day. And that was just the way things worked back in that world. And he published many papers about some of the discoveries that were pursuant to some of the work that these ladies did, and he would consistently give them credit in the body of the article. Yeah, there's a question?
Yeah, I just want to ask real quickly, it looks to me that from the dates that maybe these men were hired because it was the First World War, and the men fighting. Is that possible?
He had them. He had women employed in the late 1800s as well. So it wasn't. Yeah, and he actually died in 1918, not because of the war. I don't remember. I read it. I just don't remember if it was influenza. You know, the big epidemic that swept the globe. I don't know if that was the reason for his demise or not. But anyway, Harlow Shapley took over after him. Some of you have heard the name Harlow Shapley, a famous astronomer. But Edward Pickering is the one who really employed and deployed these female computers in the process of cataloging and understanding the stars. And here's a picture of the Harvard Observatory today, still around. And I think this red brick building, I believe that's the building a lot of them worked in. All right, so another couple of famous people. Could we try to close some of these
I can get
blinds
that.
here? It's a little washed out. So Henry and Anna Draper. Henry Draper, interesting fellow. Henry Draper was an amateur astronomer. And an amateur is someone who does a task for the love of it without being compensated. But he was very much professional in his approach to amateur astronomy. So amateur does not mean incompetent or untrained necessarily. He was actually the dean of a medical school. He was a doctor, Dr. Henry Draper. And he loved astronomy. In fact, he was his position as physician and dean was lucrative enough that he retired early and dedicated most of his time to his study of stars. And one of the things he was studying was he was trying to find out the chemical composition of stars. So there were people who, Fraunhofer and whatnot from Germany, had looked at the different colors of light coming off of burning elements or light absorbed by gases of different elements alternatively, and had started this work of trying to understand what something was made out of by looking at the way it interacted with light. Henry Draper was the first person known in history to take a picture of the spectrum of a star. Right? So just like you can take sunlight and move it through a prism and splash it out into a rainbow swath of colors, you can do something similar with starlight. So he's the first known person to take a black and white photo of the color spectrum of a star. Why is it useful to have a black and white spectrum of that? Because it still goes from red to ultraviolet, or red to violet, and so you know where the colors lie along this spectrum, even though it's just shades of gray, right? Well, he up and died about 1882. I think he was in his early 40s when he died. Retired early, I told you that. And his widow, Anna Draper, was cognizant of this undertaking, this project that he had to catalog the stars and figure out what they were made of. And so at the time, Harvard College Observatory was unfunded by the college itself. So the director had to go out and beg for money, right? That was one of his jobs. And that was one of the reasons he wanted to hire staff with modest pay, right? He didn't have a whole lot of money available to hire staff. So Anna Draper gave her husband's telescopes to Harvard Observatory and endowed them a significant endowment in order to complete his work of making a catalog of the stars and trying to understand what they were made out of. And that work eventually resulted in something called the Henry Draper Catalog. And the Henry Draper, here's a picture of, this is not the first stellar spectrum taken by Henry Draper, but it is a stellar spectrum from about that era. It shows, what is that, Omnicorn Ceti, that's the name of a star in the Cetus constellation, and then Alpha Canis Majoris, that's the brightest star in the Big Dipper. No, Canis Major, that's, yeah, oh, Minor, yeah, Canis Minor, sorry. And so these are spectrums of a couple of stars in the night sky. And you can see these dark bands in here. Anybody not familiar with a spectrum and what this, in general, what this is entailing? I can explain. Okay. So when you take the light, like of a candle flame or the light of the sun or many other kinds of light, and you put it through a prism, as long as the resolution of the optical interaction with the glass and the slit that you shine it through to make sure that you've got a really finely controlled optical path for your instrument, what you'll end up seeing is these lines. They're either bright lines, like, let's see, I think I've got a laser on here somewhere. There. You'll see a bright line like that. That's called an emission line. So there's some atomic element that sees a lot of, the electrons in that element jump around a lot, and when electrons jump, they emit light. When they jump from a higher level to a lower level, they emit light. And similarly, you see absorption spectrum. Here, a dark line is where there's some kind of gas or atom that the light moves through, and that particular element absorbs a particular color of light. And so there's the fingerprint of many elements in this. And there's only about 90 elements that occur naturally. But if you get a star that has all kinds of elements in it, you get a really complicated pattern, right? Lots of stuff to decipher in here. So I was talking about the Henry Draper catalog. This is an image of the Pleiades, the seven sisters. You can actually see 6 stars. There's a wonderful story to be told really quickly, tangentially. Cultures throughout known history have called these the 7 stars, or the 7 sisters. But you can only see 6. And even back in the times of ancient Greece, you could only see 6. But they were known as the 7 sisters. So there's this wonderful piece of speculation that this may be the oldest recognized asterism, is what they're called, collection of stars that gets a particular name. Like the Big Dipper is an asterism, right? The constellations are asterisms. But so is this, the 7 sisters. It's a kind of asterism. And there's this notion that this may be the oldest asterism in human history because about 20,000 years ago, one of these stars is a double star, and about 20,000 years ago, you could have visually discerned between that double star. It didn't just appear as one bright spot of light, so it may have been 7 stars in the very distant past. Anyway, cool little story. But I've circled a star here. It's not pulsing like that up in the night sky. But I've circled it to emphasize it, and you'll notice that these are different names of that star depending upon the cataloging effort that recorded it. And you'll see underscored there is HD 23408. That's from the Henry Draper catalog. That came directly, that designation came directly from the work of these computer women. Harvard computers, I've already spilled the beans. They didn't look like that. They look more like this. Okay? And we are fortunate today we have a computer with us, a human computer. Not a lady, as far as my interactions with this person have made clear. But anyway, Terry here in the front row, want to raise your hand, Terry? Terry was a computer working for the U.S. Army, was it?
Yeah, it was Cold Read's Research and Engineering Laboratory for the University of Illinois. We supported it up in Wilmette. Went up the Arctic, got the samples, brought them back, analyzed them.
Okay, so,
50s.
yeah, in the 50s. So,
Late 50s, yeah, like late 50s.
thank you. So, yeah, he was analyzing data taken by scientists at working as a human computer. He told me before the program today that all he had was an adding machine, essentially. And so he had to do a lot of calculations. And then he actually discovered, this was a really cool part. Thanks for sharing this, Terry. he discovered, kind of by looking at the data, that the hypothesis about how that data related to reality was in error, that there were some information encoded in the data that the scientists had missed. And so you highlighted that and you moved that thought up the chain, and it turns out he was right. So the same kind of thing that these Harvard female computers did, which is they'd look at the data and say, you know, I have a brain, and I understand what a star is and what a spectrum is, and there's something funny going on here, and sometimes they'd even form a hypothesis about it. And so Pickering would often credit them when he would write up some of the discoveries. But he never included them on the byline. His successor, Harlow Shapley, did. Here's a picture from 1913. Remember, he died in 1918. So here's a picture from 1913 of Henry Draper, Pickering, Charles Pickering. And that's him. And here are some of his computers, some famous ones in here that I'll talk about in just a minute. All right, so when we try to describe the stars, what are some of the things we can describe? We can describe their position. We can describe their brightness. We can describe their color. Different stars have different colors. Some are bright white, some are dim and red. Some are bright and red, like Betelgeuse. It's a fun word to say, isn't it? Don't say it 3 times. And there are other things you can do to describe stars as well. You can, as you collect more data and as your scientific techniques advance, maybe we can start talking about the distance to different stars, right? The ancients, a star was a star. Stars were as distant as stars are. The idea that different stars are different distances might have occurred to them, but they had no conceivable way of figuring that out. But now we have some techniques to help us understand the distance, motion of stars. I talked about the wandering stars, which now are known as planets, and they're much closer than other stars. But the motion of stars over vast stretches of time, you can start discerning the motion of stars as they gravitationally interact with each other. The variability, right? The ancients thought that the universe was, or the heavens were static and unchanging, except for the wandering planets. And one of the things that was discovered in the 1800s was that stars could be variable. Their brightness could vary over a period of months, weeks, or years. And then finally, the composition of stars, right? I showed you the spectrum. So these are the questions we can ask in the modern era. That little orange bar separates some of the ancient questions that could still be answered partially by looking at photographic plates, and then some of the more modern questions that we're able to ask about stars. And a lot of this stuff, especially on the bottom, those questions started being asked and answered by these Harvard computers. And then the life cycle of stars. Do stars come and go? Are they, in fact, permanent? So here's a picture of a couple of the photographic plates. I talked about them. One of them has been marked up by one of the computer ladies. So this, this is an image of a glass photographic plate taken of the Andromeda Galaxy, with a bunch of stars in our own galaxy here in the foreground. And these dark colors around the edges are, you maybe have seen that in some of the photographs you take. This is a vignetting. It's caused by just properties of the light falling off towards the edge of a lens. And then here's the Andromeda Galaxy again, and different stars. And these are the notations made by the hand of some of those ladies. Look at the meticulous work and the notes taken about these stars. Just amazing amount of work on just one photographic plate. And this was a lady who was particularly Fleming. This is Miss Fleming, Wilhelmina Fleming. She was a Scottish immigrant. And she was Edward Pickering, the director. She was Edward Pickering's housemaid. And he knew that she was a smart lady and meticulous. And so he hired her, instead of cleaning house, why don't you help me with my astronomy? And it was a great idea. She was one of the first computers that he hired. She was exacting, dedicated, meticulous, and she led the whole classification effort for the Henry Draper catalog that I talked about. So she was in charge of standardizing and overseeing the compilation of data that went into this Henry Draper catalog, which is still in use today. It's like 90 volumes of data about different stars. So this was the lady in charge of that. One of the things that she did was she was this effort that Pickering led with the Harvard Observatory Telescope led to the first picture of the Orion Nebula. So you may be wondering why in the intervening century the Orion Nebula has gone from a dark smudge to a bright smudge. That's because this is a photographic negative, as were those other plates I showed you, right? It's the way photography works is the light causes a chemical reaction that actually darkens the pigment on the photographic emulsion. And then if you want to get the positive of that, those of you who are familiar with the way darkroom techniques worked back in the day before digital cameras, you would turn that into a positive. Well, here's an image out of a digital camera today from a little backyard telescope of the same object. So amateur astronomers can do at least this good now with their own equipment. There I've moved it so it's in the same orientation. Hopefully you can spot the similarities there. It hasn't changed much in 150 years. The total number of plates taken by the observatory and analyzed by these women is something like 550,000. 550,000 plates meticulously cataloged and analyzed. And not just plates that showed pictures of stars, but also pictures of stellar spectrum as well. And we'll get into more of that in a minute. And the whole effort from the Harvard College Observatory persisted from 1886 until 1973. Right? That was before digital cameras, right? So this effort was nearly a century-long effort, 550,000 glass plates. And they're still stored in a fireproofed, waterproofed, hurricane-proof, bomb-proof installation in Harvard, and people still use these for research today. Remember one of the things I talked about was stellar motion? Well, if you've got a picture of a star from 150 years ago, well, 105,000 years ago, whatever, and you compare it to a picture taken today, right? If you were to compare these two pictures in meticulous detail, you may discover that some of these stars have just barely moved a little bit. And that's interesting scientific information. All right. So
Or disappeared, right? Or disappeared.
that's rare, but it does happen. And when it happens, it usually catches worldwide attention from astronomers and physicists and astrophysicists and the general public and news reporters. There was recently a star that just literally vanished. Just boop, it's there in one photograph and gone in a subsequent year, just gone. No supernova, didn't leave anything behind. They think it might be a rare instance where a star just collapsed into a black hole without going through any kind of tantrum in the interim. Anyway, yeah, stars can disappear. It's very rare, though. So this is Nature, famous scientific publication from, what is that, 1887? And down here, it talks about the Henry Draper Memorial and the effort to compile this catalog. Here's on the left is a picture, a black and white picture of the stellar spectrum. There's this, I believe this is probably several stars stacked up on the same exposure plate. You'd move a little knob, and it would put different stars in the exact focal point to go through the spectrometer. And here's a modern color picture of various stars and the spectrum. You can see the bright and dark features more clearly here. And then this one was really exciting. I just added this one. Oh yeah, zoom in a little bit, help my audience. And you can see, one of the things that's interesting about this, you can see the names of different elements associated with some of the lines you see. So you see the helium line, the carbon line, the oxygen line. And then if you get a more complicated spectrum like this, you can identify the different elemental signatures. Iron makes a lot of lines. Iron has a lot of electrons in it compared to hydrogen and helium and carbon and nitrogen and whatnot. So iron has a lot of atomic transitions possible, and so it leaves a lot of mess in your spectrum. Yeah, you had a question? The question is, are we looking at the black lines in the spectrum or the colored lines? That's a good question. It kind of depends on what it is you're looking at. So typically what happens with a star is that the surface of a star is somewhere between 3,000 and 50,000 degrees Kelvin. Our star is about 5,000. The surface of our star, the sun, is about 5,000 degrees Kelvin. At the temperature associated with the surface of a star, even a relatively cool star, molecules dissociate into their respective atoms. And when you have individual atoms floating around in the atmosphere and they're bombarded by radiation from the star, typically light, so that there's a notion of a black body radiation. You just take anything. It could be a white marble, it could be a black lump of coal, it could be a slug of iron, it could be a piece of glass. You heat it up hot enough and it'll emit light, right? And that light is only dependent upon its temperature. It doesn't depend upon the chemical composition, right? But if you start, there are certain circumstances where the outer layer of substance of that emitting object, and especially if there's any kind of outgassing, you heat it up hot enough that it starts outgassing, the gas between your instrument and the hot object absorbs some of that light in a characteristic way. So the black lines are what's called absorption spectra, and that's actually measuring the presence of the elements in the atmosphere of a star. And every star has an atmosphere, and by looking at these lines, you can say what kinds of elements are present in the atmosphere of the star. And there's no reason to think that the bulk of the star, to a first approximation, is any different than the atmosphere of a star, right?
We should note that this is,
Want to wait for the microphone?
they're called Fraunhofer lines.
Yes, yeah.
And they're called Fraunhofer lines, and notice the sodium line. That's the common denominator that we use in calibrating everything. You line up the sodium, and then everything else falls out from that. And that's called the sodium D line.
Thank you.
I try to keep my sodium lined up.
Scott, just one comment. I mean, we usually talk, you know, the question was about the colors. And I think that's just an easy way to put frequency or temperature. You put cold on the left and hot in the front. But we always talk about them in terms of the different ranges, like infrared and ultraviolet and all that. I think putting the color on the horizontally just simplifies it rather than talking about 650 nanometers or something like that
Right.
nobody understands. It's just a simplification for general
Yeah.
public. But basically, it's cold on the left, hot on the top, low frequency on one, high
Right.
on the other, that type of thing.
Yeah, it's one of the things I wanted, and you jogged my memory. I wanted to mention this today. This notion of, you know about the notion of something that's red hot, right? And you talk about painting a room. You paint it with red, and that makes the room warm, right? If you paint it blue, it makes it what? Cold, right? So there's this intuitive notion that a lot of people have that red is warm and blue is cool. Well, it's actually the opposite in physics and the physics of light. Red light is lower temperature, lower energy, cooler. And blue light is higher energy, hotter. So a red star will be a cooler star than a blue star. It actually gets white hot, as it were. Yeah, the flame is blue in a hot stove. Thanks, Terry. All right, Wilhelmina Fleming, another computer. Oh no, so this is the same one. She worked as the maid. She developed the simple stellar classification based on spectrum, and she just chose the easiest. There were all kinds of different ways that stars were classified up until then, and she said, you know what? I'm just going to throw all those out the window, and I'm just going to do a simple classification. We're going to go A, B, C, D, E, right? And it worked. All right? So based upon the color of the star, or the spectrum of a star, she came up with, and the brightness, she came up with this way of classifying the stars. All right? A, B, C, D, E, F. It's hard for me to say that because I know how it's changed. At this point, figuring out stuff about the stars is a lot like butterfly collecting. Oh, this one's big, this one's small, this one's blue, this one's red, right? This one is in this part of the world, this one's in this part of the world, this star's in this part of the sky, this star's in this part of it, right? It's butterfly collecting. In my first book, one of the things I write about is that science typically begins as butterfly collecting or stamp collecting. Right? How is this thing different from other things? What are the things that make it different than other things? How many different kinds of things can apply to this thing compared to other things, right? You start compiling this list of the features of the thing that you're investigating long before you have a hypothesis about what causes these features to be real, right? To differ from one another. And this is in the butterfly collecting era of stellar cataloging. What are they? Where are they? What color are they? How big are they? How bright are they? How far away? Well, they didn't really do a lot of that yet. All right? So, A, B, C, D, E, F. Different butterflies have different names, right? We could have given different kinds of stars different names, you know, Orville and Henrietta and whatnot. No, just A, B, C, D, E, F. Simple as you get. All right, she also discovered this creature. This is the horse that lives in the sky. This is in the constellation of Orion. It's called the Horsehead Nebula. Reasonably enough. Sometimes astronomers, I don't know, some of the other physicists, they get whimsical, you know, up and down, top and bottom quarks and whatnot. No, it's the freaking horse, right? Horsehead. You call it as you see it. And here's the photographic plate she used to discover it. It's circled right there. That is the Horsehead Nebula. That's the belt of Orion, these three stars, and the Horsehead Nebula hangs off the bottom of this omnicorn or whatever, this star in Orion. That is the photographic plate that she used to first scientifically describe the Horsehead Nebula. It's how meticulous this work was.
What makes it actually be a nebula? Just so everyone understands that. What makes it a nebula in nowadays terms?
Let me go back. So this is a dark cloud of gas and dust that's interposing itself in front of some glowing hydrogen that exists in the background. So the constellation of Orion is just littered with stellar debris and gas and dust and whatnot throughout the whole constellation. The Orion Loop, I think it's called. Something tells me I didn't quite get that right. But anyway, the constellation of Orion is just smeared with garbage. Beautiful garbage, right? And so this is a dark nebula in front of a bright nebula. A nebula is just, it's not a star. It's some kind of extended feature. Astronomically, stars are points of light. No matter how much you magnify them with all but the very best telescopes in the world, with the very biggest stars known, to a first approximation, stars are always just points of light. Even the brightest star you can see is just a point of light. No matter how much you magnify it, it's just a point of light. Well, these nebula are extended objects. How can you have extended objects out in space? And these are clouds of gas and dust and whatnot.
Yeah, interesting. You pointed out nebulas, and it's a topic I hadn't thought about. Are they gravitationally bound, like a star or a planet or even a black hole, or are they just there? Do you know?
Good question. Did everybody hear the question? Okay. I think I need to do another Science Sunday about that. Generally speaking, they're gravitationally bound, certainly within the galaxy in which they exist. And there's pressure waves and spiral arms and regions of star formation, and there's a thing called the Jeans mass. And it's just, yeah, let me talk about that sometime in the future. But yeah, they're mass and they're clumpy, so a little bit of gravity there. Okay. All right. Also, Wilhelmina Fleming, the maid. Here's a big, bright, brilliant, white, hot star. Here's a star kind of like the sun, smaller. And then here's the tiny little blue dot, tiny blue dot. That is the corpse of a star called a white dwarf. I'm not going to talk in detail about it today, but Wilhelmina Fleming is the first person in history known to discover a white dwarf. You'd think with all these discoveries she would get a Nobel Prize. Nobel Prizes existed back then. No. Nope. Wrong gender. Right? Shall we remember her as a maid? Shall we remember her as a computer? This is her tombstone. Astronomer. Damn right. All right. Henrietta Swan Leavitt. Leavitt? Sorry, I read these words. I don't hear them often. She specialized in variable stars. I talked about those a moment ago. And particularly, there's a kind of star where the brighter it is, the longer it goes between getting brighter and getting dimmer. Right? So its absolute brightness is correlated with its period. A dimmer Cepheid will have a shorter period. Blop, 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 blop. A brighter Cepheid will have blop, 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 right? All right, they change brightness through time. And she specialized in identifying these Cepheid variables. Pretty cool. But that's not where she stopped. She also developed this notion of the correlation between working with Pickering, between brightness and period. If you know how bright a star is intrinsically, how many photons per square meter are emitted from its surface, and you move it 50 meters away, it has one brightness. If you move it 500 meters away, it's much dimmer, right? So if you know the inherent brightness of an object, you can tell how far away it is just by looking at its apparent brightness. Does that make sense? A flashlight that's shined into your eyes is much brighter than a flashlight held half a mile away. So wouldn't it be cool to know how bright a star is intrinsically? How would you do that? Well, with these Cepheid variables, you can measure its period. And it has a particular chemical fingerprint, too, the spectrum of it, so you can identify them. And if you can measure the period of this variable star, you automatically know its brightness. And so now you can figure out how far away it is by how relatively dimmer it looks compared to other Cepheid variables with a similar period. This was the first step in what's called the cosmic ladder, figuring out a distance scale, how we can measure the distance to stars. I told you this is one of the measurements that came about in the late 19th, 20th century. Finally, we could start talking about how far away stars were, and this was the key step that allowed this to happen, and it was largely because of this lady's work. By the way, prior to this point, they picked just a random star to be the guidepost, what do you call it, the reference point for stellar brightness. And they decided that the star Polaris, the North Star, which you can see all year long, the star Polaris had magnitude in these funky numbers that scientists use, of 2.1. 2.1 is the magnitude of Polaris. Done. Now we can compare every star in the sky to Polaris, and we can figure out their magnitude. Makes sense. Turns out Polaris is a Cepheid. So its brightness varies over time. So depending on what night you were comparing the brightness of another star to Polaris, you might be off a little bit. Oh well. Thanks, Henrietta. All right, so this is the ladder, right? The cosmic ladder. Cepheids allow us to measure distances. They're down here. Cepheids allow us to measure from about 1,000 light years away up to about 10 million light years away. Individual Cepheid stars have been resolved on photographs of nearby galaxies. In fact, they played an instrumental role in convincing scientists that other galaxies are not clouds of gas and dust in the Milky Way, but that they are separate islands of stars. The Cepheid variables, because they could be resolved in distant galaxies, and they were incredibly dim, told us that those galaxies were millions of light years away. This was a stepping stone to understanding the true scale of the universe. Thanks, Henrietta. Oh, this is the Andromeda Galaxy in a more modern color photograph. Beautiful critter. All right. Miss Leavitt, who gave us the first big rung, actually the second, parallax is the first, but I don't have time to talk about that. Miss Leavitt, there's this accolade from this gentleman, Sobel, no, that's the book I read. I forgot his name. It'll be here somewhere. Oh, yeah, there it is. From
Professor von Zeipel of Uppsala.
Goethe Mittag, Leffler. Honored Miss Leavitt, began his letter to her. What my friend and colleague Professor von Zeipel of Uppsala has told me about your admirable discovery of the empirical law touching the connection between magnitude and period length for the Cepheid variables of the Little Magellanic Cloud has impressed me so deeply that I feel seriously inclined to nominate you for the Nobel Prize in Physics. About time. This is the guy largely responsible for getting the Nobel Prize awarded to Marie Curie. Right? So he was a fierce advocate of equality. So he sent this letter to her, nominating her for the prize in 1926. Miss Leavitt had died in 1921. So it didn't happen. The prize is not awarded posthumously. Right, our next lady, Annie Jump Cannon, star classification expert. She herself personally classified about 350,000 stars. Whew. Sorry for the small font. I'm usually better about that, but I'll read it to you. She studied, she got an undergraduate degree in physics. She was not able to find a school that would admit women into a PhD program. But she got an honorary doctorate for her work. And she was curator of the photographic plate library. And the other lady was in charge of the Henry Draper catalog. This was a lady put in charge of the photographic plate library. And she found some logical reasons to rearrange the A, B, C, D, E, F, G, right? She found a reason to rearrange that based on star temperature and composition. And so she gave us our modern, still used 100 years later, our modern designation, which is OBAFGKM, from bright white to blue to yellow and whatnot. We're a type G star, known as a yellow star. By the way, if you're out in space and you try to look at the sun, don't do it, it'll hurt your eyes. But if you did, you'd find that our star was white. It's white, it's not yellow, it's white. It's because our eyes have evolved to be sensitive to the colors emitted by our star. And it looks yellow because of the scattering of blue light from the atmosphere. That's why the sky is blue. Takes out the blue light, what's left looks like red and yellow. That's why the sun looks yellow. Anyway, she rearranged this. There's I learned it, and people who study astronomy learn, O, be a fine girl or guy, kiss me, OBAFGKM. There's some talk about changing this. I came up with my own the other day. Obama for great America. For great, Obama, OBA, for great Kingdom America. How about that? You like it? Oh, well. By the way, Annie Jump Cannon made it into a comic book. 1949, The Four Dooms. Wonder Woman, number 33. Annie Jump Cannon made an appearance. She and Henrietta Leavitt, by the way, were deaf, mostly deaf. Amazing. There's a play about Henrietta Leavitt, or Annie Jump Cannon. I think it's Leavitt. A play about Henrietta Leavitt called The Silent Sky or something like that. All right. Boy, I'm running out of time. Is this fun? It's fun? All right. Antonia Murray, stellar classification. She specialized in spectrums, right? So what happens if you see a spectrum that looks like this? Did you see what I did there? Let me replay that. All right, stellar spectrum, simple. This is hydrogen. What happened? What do you see now?
It's offset. It's offset.
Yeah. Why is it offset? Well, maybe there are two stars near each other. One of them's moving. So one of the Doppler shift, right? Doppler shift happens to light as well. And so if there are two stars next to each other and they're moving relative to each other, they may have their spectrum offset a little bit because the motion of one or both of them causes the spectrum to be offset. What if you see something like this over time? Right, a binary star. She specialized in finding the spectrum stars, and especially binary stars, and these are called spectroscopic binaries. Can you tell why? Right? You can't discern them from a telescope. You can't look at them and see two stars, but if you look at their spectrum, you see it. Spectroscopic. This is the spectrum of the sun, going from red to violet. It should be one long strip, but it's folded for your convenience. Look at all the element signatures in there. Cecilia Payne-Gaposchkin she was inspired by Arthur Eddington's lecture on relativity to study physics and astronomy. Harlow Shapley, Pickering's successor, encouraged her to write a PhD thesis. She wrote a PhD thesis about the chemical composition of stars, and she found that hydrogen was 1,000,000 times more abundant than any other element. And people didn't believe her. She didn't believe her at first. But it turns out that she was right. Here's a couple of books I used to inform this lecture. Sorry, I'm rushing because I'm long-winded. Here's Omega Centauri. This is a globular cluster. They think it's actually the heart of a dwarf galaxy that interacted with the Milky Way. Here's a Hubble picture. Let's take this Hubble picture and let's sort the stars by color. So one of the first things you can do when you're looking at stars, remember, you just sort it by color. So what happens when we do that? We can, come on video, I'm rushed for time here. So we sort the stars taken from this bejeweled cluster by color. You separate the blue ones and the white ones and the red ones and the yellow ones, and then you can also sort them by brightness. You sort them by color and then by brightness, and you end up with a graph that looks like this. And this is ubiquitous in astronomy. This looks important, right? It's important enough that most of the stars lie along that main sequence, and then you have the red giants, and I'm going to talk more about this in just a second for about 10 seconds. So this is the ubiquitous Hertzsprung-Russell diagram. And by the way, Henry Norris Russell was one of the people who argued with Miss Leavitt about, with Cecilia Payne about whether stars were made of hydrogen or not. He thought it was ridiculous. It's a stupid idea. Stars are made out of the same stuff the Earth is made out of. Silicon and iron and magnesium and calcium and oxygen. Hydrogen, water. She said hydrogen is 1,000,000 times more abundant in stars, and she was right. So Henry Norris Russell had to eat his cake or hat about that. And this is the HR diagram. This is the way to scientifically specify this. This is the sun. This is the location of the sun. Put a lot of effort into this animation, so you got to see it. Next, we have what's called the main sequence. That's where most stars lie. Stars right there are burning hydrogen as their primary fuel. And then when they run out of hydrogen, there's leftover helium in their cores. They start burning helium. Helium releases more energy when it's burned, but it takes more gravity to squish it in the first place. It makes for a bigger star. Those are the red giant, called the red giant branch. And then next is our sun, the star, will over couple billion years move into the red giant branch. And then what happens? It falls down and becomes a white dwarf. It puffs out its outer layers, only the white hot core is left, cooling off. And then the other thing, the bright blue stars turn into other kinds of red giants, and those usually end in a supernova. And then when they're left, they end up making a black hole or a neutron star. Speaking of, this is the last one. Speaking of neutron stars, this lady discovered the first pulsar, which is explained by the rotation of a neutron star. She discovered it in 1967. The Nobel Prize for this discovery was awarded in 1974, but not to her. She was very polite about it. I believe it would demean Nobel Prizes if they were awarded to research students except in very exceptional cases, and I do not believe this is one of those cases. Very humble about it. One of many times Nobel Prizes have not gone to accomplished and innovative women. She helped build the stellar theory, and she deserved it. The astronomers, the women who helped us understand the stars. That's it. Sorry I rushed there at the end. Thank you for attending.
Any questions or comments? Yeah.
You can go ahead. I'll repeat it. I'll repeat your question for the video. All right.
Okay, I was just going to say that the Seven Sisters,
Uh-huh.
that story, which, by the way, the moral of that story is girls stay away from men you don't know because they will rape you,
Yeah.
because the story is about 100 chasing 7 girls. I'm just wondering if you happen to know more about when that star could no longer be seen, because that story is so old. I know it's
Right.
been in Aboriginal culture
Yeah,
for
you can-
probably 50,000 years.
You can look. You can Google different stories about that, about the Pleiades, the Seven Sisters, ancient constellation, and you'll find out about that.
So we can assume the star disappeared.
No, it didn't disappear.
I
It
mean,
was
it didn't disappear, but couldn't be seen.
correct, even in the time of Greece.
At least about 50,000 years ago, something like that, because.
I
know
think it was 20 or 30,000, but yeah, a
Okay.
long time ago.
Okay.
All right, another question.
I was just going to ask, what makes a Cepheid star change its brightness, pulsate like that?
Complicated thermodynamic processes. There's all kinds of competing forces in a star. Depending on the size and mass of a star, you get big convective currents, like in a boiling pot of water, and those convective currents take time, right? And so that can lead to physical pulsations in the size of the star. And if you decrease something that's got the same total energy output, you decrease the size of it, it looks brighter, right? Its energy per surface area goes up because it's smaller, right? So it's just some thermodynamic stuff. I've got a book on astrophysics that explains it, but you have to get into the equations of the thing.
Thermodynamic stuff.
Yeah.
Okay.
Yeah, our own star is very slightly variable, the solar cycle and all that. Yep. Yeah, yeah, most stars probably have some kind of rattling and vibrating to them. All right, we got to get out of here. There's another event happening in here, but thank you very much. We'll see you in a couple weeks.